Hi class, today we're going to start chapter 7. We are done with chapter 6. Now, we only have 3 topics left for the whole semester. They're kind of shorter, more isolated topics, so we'll treat 2 of them today, and then on Tuesday we'll cover the 3rd topic, and we'll have time to start reviewing on Tuesday, and then Thursday will be completely a review day, and then of course the final exam will be on Friday, May 8th. So, first we're going to cover section 7.1 and the toolbox for chapter 7. Chapter 7 is entitled Systems of Linear Equations. Now, we've worked with systems of linear equations where we had 2 variables. Usually we called them x and y, although they could have any names. And because we had 2 variables, we had to have 2 equations involving those variables in order to solve the system, either by elimination or substitution or by graphing. Okay, let's step it up a notch today. Let's introduce a 3rd variable. Now this is all in your toolbox on page 509. Here's a linear equation in 3 variables, x and y, and now z. A, B, C, D, they're just constants. So an example would be 2x minus 3y plus 4z equals 5. That is a linear equation in 3 variables. Now we know that a linear equation in the xy coordinate system is a straight line, hence the name linear. We keep the name linear here, but the graphical meaning of this is no longer a line. It actually turns out to be a plane in 3-dimensional space. If you consider the fact that we're adding a 3rd variable, then we are adding a 3rd dimension. And if you go on to future classes such as calculus, you would draw 3-dimensional graphs like this. Here's your x-coordinate, here's your y-coordinate, and your y-axis, your x-axis. This is your z-axis. And that is a rendering of 3-dimensional space. Now the diagrams in the book are much nicer. I won't even attempt to duplicate them. Look at figure 7.1 on page 510. There is something that can happen with 3 planes. And if you had 3 of these linear equations with 3 variables, each one would be a plane, assuming they are independent of each other, independent equations. So you'd have 3 planes floating around there in 3-dimensional space. So looking at the picture, in 7.1, you see that if the planes are not parallel, then they're going to intersect each other. And actually, if you look and you see where the green plane intersects with the purple plane, the intersection of 2 planes is a line. And then the blue plane goes through and hits those 2 planes, and it hits that line of intersection in one spot, so the final intersection there is a point. So in this case, algebraically, we are going to have a unique solution. We're going to get one value for x, one value for y, one value for z that solves all 3 equations. And we see that we have one point of intersection. Now in figure 7.2, you see that the first 2 planes, whichever 2 you pick, intersect in a line, but then the 3rd plane goes right through that line of intersection. as it could be called. So there you're not going to have a unique solution. You're going to have an infinite number of solutions. You're going to have a line of intersection between those three planes. So that's the second thing that can happen with any three planes floating around in three-dimensional space. Now look at figure 7.3. The blue plane hits the green plane and it hits the purple plane. But the green plane and the purple plane are parallel. Right? We say planes are parallel if they never touch each other. So the plane of my sheet of paper and the plane that I'm demonstrating by moving my hand, they could be parallel. They would never intersect. So in this case, you're going to have no solution because there is no intersection between all three planes. Two of the planes intersect, but not all three. All right, so those are our three geometric possibilities. Let's look at example 5 and think about the algebraic side of things here. Now this is a big, long example. I'm going to fill up my board here probably twice doing this big example. All right. In this example, in part A, we are given an equation, a linear equation in 3 variables. Actually, let me read the problem in the book. I believe we're given 3. Yeah, we have a system of 3 linear equations in 3 variables. The first one is this. And the question that we're asked is x equals -2, y equals 0, z equal 1. Is that a solution of the system of all 3 of these equations? Well, what we're going to do is substitute these values into each one of the 3 equations. I wrote down the first equation. Oops, y is 0, z is 1. There's my question mark. Is that combination of x, y, and z going to work in here? Yes, it checks out. Let's write down the second equation, substituting in those values. All right, there's the second equation, and I've substituted in x equals -2, y equals 0, z equals 1. And is it going to check? Yeah, okay. Finally, the third equation. Let me just substitute right into it. Will this work out to be 1? Yep. Okay. So this combination of x, y, and z works in all 3 equations in the system. Therefore, it is a solution to the system. And each one of those 3 equations represents a plane in 3-dimensional space. So that means there is one point of intersection between those 3 planes. In other words, it's figure 7.1. All right, so that's what we needed to know from the toolbox. And I guess I didn't need more than one board, but I will pretty soon. Yeah, example 1 in the next section, that's the big one. Let's look at section 7.1. Systems of linear equations in three variables. I'll just call it linear equations in three variables. I just showed you how a solution behaves, but can you find solutions on your own? Well, as we noted, I mentioned when we started class, we did problems like this a few weeks back. This is a system of two linear equations in two variables. And we know what to do. You can, one of the approaches is you can use elimination and get rid of one of the variables, or else use substitution and get rid of one of the variables. But somehow you got to get rid of one of the variables to get an equation with just one variable, then you solve that one. Now it turns out we're working with three equations and three variables, so you would probably expect, yeah, if we didn't have three equations, we wouldn't be able to get rid of all the variables. So let me ask you this. Suppose we had n of these equations with n different variables. Could you solve it? Yeah. Basically, you need one linear equation to eliminate each of the variables, and you could keep picking them off if you were patient enough and had enough time, and eventually solve the system. Let's look at example 1 in your textbook on page whatever it is there, 513, page 513. We're asked to solve this system. 2x minus 3y plus z equals -1. Oh, I see, okay. It's a linear equation in three variables. And of course it's linear because all the variables are to the power 1, right? The invisible 1 is the exponent there. That's why we call it linear. Let's get this out of our way. The second equation looks like that, another linear equation in three variables, and then a third one. 3x plus y minus z equals 9. Now I'm going to show you how to do this in a slightly different way than the text, but it's mathematically equivalent, and I think this is a little easier. We don't have to learn a new technique this way. Let me clean up my board. I'm going to do a bunch of work here. First thing I noticed was if I took the second equation and multiplied it by -2, I could arrive here. I'll work with the first equation. I'll write that down again. Then I'll take the second equation and multiply it by -2. And the reason I did this was so that I'd get a -2x here and a positive 2x there. So now I can add. And of course this is the process of elimination. We learned this a couple weeks back. I add and I get -y minus 3z equals 5. So alright, now I have an equation in just two variables, y and z. If I could get another equation with just y and z in there, then I'd have the problem that we learned how to do several weeks back, right? Two equations, two variables, we know what to do. So, I need to eliminate the same variable again. Let me combine the second equation with the third equation. And I'll go over here and keep working like this. If I have the second equation, x minus y plus 2z equals negative 3. And then I'll write the third equation underneath it. And you can see what I'm getting ready to do here with the parentheses. I'm going to multiply this top equation by negative 3 so that I get negative 3x and I'll be able to add things up. Of course, then I have to do it on the right-hand side too. So that gets me to here. Minus 3x plus 3y minus 6z equals positive 9. Right? That's what I get when I multiply through by negative 3 here. I get down to here. Let me fix my bracket, my curly bracket. Okay. And I'll leave the lower equation here alone. All right, so you have to take a different combination of equations. First we use these two equations, now I'm using these two, right? You wouldn't get anywhere if you just used the same two equations over and over. And I've got this set up now to where I can add and eliminate the same variable, x, that I eliminated up here. Oops, that's not equal, that's a minus 7z equals 18. So I have another true equation there, which involves the variables y and z. I'm in business. Now we do exactly what we did 3 weeks ago solving these systems. Okay? It's just a system of linear equations and two variables. So we solve as usual. I'll multiply the top equation by 4. That gets me a minus 4y there. You can see what I'm going to do. I'm going to eliminate y. So now I add these and I get negative 19z equals 38. Ugly numbers, but when I divide these up by negative 13, I get z equals 2. Negative 2. Because these books have a bunch of problems where the numbers work out right. So that's why it looks so nice. Now, we have figured out one variable. You could plug into one of these little equations here and get y. Right? We know that's a true fact, plugging into there. So I get negative y plus 6 equals 5, negative y equals negative 1, y equals 1. And now plug into any one of these equations and you'll figure out what x is. And then don't forget to check to make sure all your work is okay. So now you try one. Number 14 in the homework. That's on page 518. Number 14, and I'll give you a hint. The first equation is divisible by 3. And therefore it's divisible by negative 3. That might be very useful.